Hey everybody, it's Mr. Cadell. How's it going? I hope well. I'm going to tell you, I love this part of the chemistry unit. We're in 2.3 now. We need to talk about three different types of bonding today: covalent, ionic, and hydrogen bonding. There's a fourth type called van der Waals interactions. I would say read it and then forget it. I've never seen it on the AP test. Of course, it could be there, but I don't know. Don't worry about it. It's not going to be on your test in this class. Let me put it that way. Then towards the end, there's a concept called dynamic equilibrium, which is important. We'll get to all this. A lot of this should be review. One other thing I would recommend is get a periodic table handy. I will go to B1 in the back of the book. I'll have that right here. Also, hopefully I gave you this handout that has a periodic table on it. These are just pictures again from the book. We're going to be accessing this table and then some other stuff in here as well. So follow along with the handout. I'm going to tell you today, more than almost any other day so far this year, you have to get out a piece of paper right now, not only to take notes, but you've got to draw. This is not a passenger activity. You got to be active here. We're going to be drawing a bunch of atoms and how they come together, and I physically want you to draw this. If we were in class, I would give you a piece of paper and I would ensure that you did that. So here we go.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dry. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus. And the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Okay, so it's not enough to just talk about atoms and atomic structure and protons and electrons. Let's start putting them together because we need to build molecules, which will then enable us to build things within cells and then cells can be put together and so on, and then we've got life and biology from there. So this says the formation and function of molecules depends on the chemical bonding between atoms. The first type of bonding that we're going to talk about is covalent bonding. Co means two. In co, it's a sharing, cooperation. Here's the definition of covalent bonding. I don't know if you can read it, so I'm going to read it to you. It says, when two atoms each share a valence shell electron, that's the outermost electron, so that their outermost shells are filled. Here's what we mean by that. You have to look at the periodic table to see how many electrons any individual atom wants in its outermost shell. So we talked about carbon in the last lecture. How many electrons does carbon have? Well, it has a total of 6. I know that because the atomic number is 6. Well, how are they arranged? Well, it's going to have 2 in the first shell, and then 1, 2, 3, 4 in the second shell. Fine, that's 6. 2 plus 4 is 6. But how many does it want? That's the question. Well, it wants a total of 8. If I count across here, all of these, so it goes 2, 8, 8, 16, 32, something like that you learned in chemistry. But as far as biology is concerned, we're only concerned with these top 3 rows of the periodic table, 2, 8, 8. That's what you have to commit to memory. So carbon wants 8 in its outermost shell, but it has 4. Now, how could it get 4 more? Well, it could take 4, or it could share 4. And ionic bonding is when electrons are taken or given. But here we're going to share electrons. That's what covalent bonding is all about. So keep that in mind, and let's see what we can do here. So let's draw hydrogen gas and oxygen gas. Please press pause. Press pause right now. Get out your blank piece of paper and draw. If you're completely stumped, that's fine. I am going to draw them up here on the board. Well, for oxygen gas, this is oxygen, molecular gas that we see out in the environment that we breathe in and helps us burn food in the presence. Oxygen and food get burned in the mitochondria and we make ATP. So if this is an oxygen atom and this is an oxygen atom, I want to put them together. This is O2. So let's do that here. So now I'm going to draw the atoms. And first thing I have to do is I have to look at where oxygen is on the periodic table. And I see it right here. It has an atomic number of 8. So that tells me that it has 8 electrons and 8 protons. It's also in the second row down, which tells me that it has two shells. So let's make this the nucleus. I'll get back to that in a second. Here's our 2 shells. Here's the nucleus. And the reason why I'm going to make this a nucleus is because I'm going to put 8 protons, 8p in there. 8 protons is the atomic number. But I also know it has 8 electrons. And I know from this that I can count across. 1, 2. That tells me that there's 2 electrons in the first shell. How many are in the second shell? Well, a total of 8 potentially, but how many does oxygen have? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm gonna actually put this guy right here. Well, let's draw another atom of oxygen. I know that it's going to have 8 protons in the nucleus, 2 electrons in the first orbital, and 6 in the second. 1, 2, 3, 4, 5, 6. I see what I'm trying to do here. The idea is that we're sharing. The outermost valence electrons are shared with each other. And so the way that we draw that here is we're going to say that there's 2 electrons in the valence shell from this left-hand atom and 2 from the right-hand atom, and they're being shared in order to create full outermost valence electron shells. And so the way that we show that this is called the Lewis dot structure, and then I'm going to make this kind of stick diagram here, is I just draw a line between 2 electrons that are being shared. And you've seen this before, where there's like 2 sticks between maybe 2 plastic atoms here that you've built in another class. So now let's count the number of electrons in the outermost shell in this oxygen atom, 1, 2, 3, 4, 5, 6, 7, 8. Let's count the outermost number of electrons in this valence shell of this atom. 1, 2, 3, 4, 5, 6, 7, 8. Is everyone happy? There's 8 protons here, and there's a, okay, nope. Anyway, the valence electron shells are full. They wanted 8. I knew that they wanted 8 because it was in the second row here, and 8 is how many they need in order to have a full valence electron shell. So this is how you draw molecular oxygen. Let me show you. It's here if you need to look. We can do hydrogen also. I don't think it's bad to do this as an activity. Let's do hydrogen. Go ahead and press pause. Don't look at the handout and try to draw it. So I'm also going to try to draw it here. I can find hydrogen or hydrogen atom right here in the top left-hand corner of the periodic table. Has an atomic number of 1. That tells me that it has 1 proton. I just wrote up here 1p with a plus next to it. I'm going to do it here. Let's imagine that these are the 2 nuclei of our 2 atoms. I also know that it's in the first row going across, so it only has 1 electron shell. And this one only has 1 electron shell. Now, how many electrons does hydrogen want in its outermost shell? 1, 2. But it only has 1 to offer someone else. So the electron from the right-hand hydrogen atom is here. It's going to be shared with this guy. And the electron from the left-hand hydrogen atom is going to be shared with this guy. So now, is this atom happy? Does it have a full valence electron shell? It does. How about this guy? Same thing. So they're each offering 1 atom that's being shared, 1 electron that's being shared here, so I can draw a stick between that. And this is called a single covalent bond. Single, just like oxygen would be called a double covalent bond. Oh, sorry. Here it is. You can see the Lewis dot structure and structural formula. You can see the name and molecular formula there. The electron distribution diagram, we just drew that. These atoms are sharing these electrons equally. This is called nonpolar. Now the term polar, I think of like term polar opposites or the poles of the planet. Those are things that are different than one another, or they're not the same. Let's put it that way. In this case, we have a nonpolar covalent bond because these atoms are sharing these electrons equally and having full outermost shells. And you're going to see in a moment where they're not being shared equally. Up here at the top, you'll see a single covalent bond, and you'll see a double covalent bond. So we've all drawn those things. Here's oxygen. Take a look at the little nuances there for oxygen. So if you're feeling good about this, you can draw fart gas, methane, which is being released in the Arctic as the permafrost melts up there in the kind of the marshy, boggy areas. Way up in Canada, Alaska, Russia, and the Scandinavian countries. The problem is that methane is 23 times more potent than carbon dioxide as a greenhouse gas, which is trapping in heat. So this is a big problem. So methane, you could draw that if you'd like. Here's our movie.
1 or more atoms may share electrons, thus forming a covalent bond. Electrons will spend a portion of their time associated with each of the participating atoms. A single covalent bond represents the sharing of 1 pair of electrons, such as with 2 hydrogen atoms. A double covalent bond is formed with the sharing of 2 pairs of electrons. Atoms sharing 3 pairs of electrons form triple covalent bonds between them.
Well, water. I'm going to tell you, water is super important. You ever thought about water and why you get thirsty? How people can survive like 4 minutes without air, 4 days without water, 4 weeks without food or whatever. The point is super important for life. You're always thirsty every day. Why? What does water do? And I'm going to, we're going to go over a lot of things that water does this year, but have you ever thought about what water really looks like? And here's kind of what it looks like if we were to draw it. I would like you to try to draw it right now without looking at your handout. Go ahead and try and draw water using the electron distribution diagram, kind of the way that we've been doing this. And so here, let me do it also. So here's kind of what water looks like. We're using this kind of electron distribution diagram that we've been trying to do. We've already talked about hydrogen, we've talked about oxygen, so let's fill this in. So we know that oxygen has an atomic number of 8, so it has 8 protons. Just gonna put that there in the middle, and then it has 1, 2, 3, 4, 5, 6, 7, 8. We know that it has 6 electrons in its outermost shell. You can count 6 right here. And I know that in order to be happy, oxygen wants to gain 2 more. Well, where's it going to gain it from? Probably from sharing electrons with this hydrogen atom. So we know that hydrogen atoms have an atomic number of 1. Here that is. I'm just writing a 1 with a P next to it up here. This is an 8 with a P next to it. And so we see that hydrogen has 1 electron and it only has 1 shell, and you can see that represented here. So this looks great to me. Here's our electron from hydrogen. Oh, my bad. Here's our electron from hydrogen, and it's being shared with the valence shell, the outermost one of the oxygen atom. Here's our electron from this hydrogen atom, and it's being shared here. No problem. If you count now the outside valence electrons in this oxygen atom, you see 1, 2, 3, 4, 5, 6, 7, 8. It's happy. What about the hydrogen atoms? 1, 2. They're happy. Now, this is important. If you add up all these protons, 8 plus 1 plus 1, you see that there's 10 protons in water. And if you count up all the electrons, you'll find that there's 10 electrons. So I'll write it up here. Water is electrically neutral. It does not have a charge. It doesn't have a plus or a minus next to it. It has the same amount of positives as negatives. But there's a problem. Does anyone know what the problem is? This is called a polar covalent bond. This bond right here, this sharing of these electrons. And we can draw it here. So you can see that in the outermost shell of oxygen, it's sharing 2 of its electrons, 1 here and here, with electron from each of the hydrogen atoms. But I'm going to draw this like this. What I'm drawing here is an arrow that's kind of pointing towards the oxygen atom. And that means that they're not sharing the electrons equally. This is a polar covalent bond, which means that these electrons are actually being pulled more towards the oxygen than they are towards the hydrogen. That then causes what we call a dipole, or a partial negative charge on the oxygen atom. But if we have that, what do you think the partial charge is on the hydrogen atoms? I'm going to write up here 2 little pluses, and I've written here a little minus. Now, the whole thing is electrically neutral, just like the oxygen molecule, O2, and H2, hydrogen gas molecule. Same with water, H2O. You don't put like a plus here or a minus here next to it like you do some other ions. But just understand that they have a portion of their entity which is partially positive or partially negative, and that has huge ramifications for biology. It's the entire basis for chapter 3 in the textbook. So I'm just going to draw, there's actually two of them, but let's just draw a negative right here. And let's draw a partial positive up here next to each of these hydrogen atoms. The reason why this is, there's two reasons. Number one, there's more positively charged protons in the nucleus here than either one of these, and so it's just stronger. Think of all these pluses in here that are pulling these negatively charged electrons towards it. And number two, it's because there isn't a third shell here. What we're going to find here, once we get to the ions on the other board for ionic bonding, is that these guys way over here in this top right corner, without going to these full outermost shells that you see in helium, neon, argon, these are non-reactive gases, essentially, the noble gases. They don't react with anything because they're full. They're totally happy. That's what everyone's trying to do, is they're trying to get full outermost shells. But these guys over here aren't full. Well, none of them are, but these guys really aren't full. But they have a lot of protons, and so they're going to pull electrons with a lot of vigor, and we'll get to that more in a second. But that's what's happening here. If there was a third shell here, these electrons that were being shared would be another kind of degree of magnitude out from the nucleus, and there wouldn't be as much of a pull here to create those partial positive and negative charges. Well, let's read a little bit. This says unequal sharing of electrons causes a partial positive or negative charge for each atom of on the molecule. Here's a picture out of your textbook. You can see those partial positive and negative charges there. This is called electronegativity. It's an atom's attraction for the electrons in a covalent bond. The more electronegative an atom is, like those ones way over there on the right side, but not on the farthest column of the periodic table, the more strongly it pulls shared electrons towards itself. This unequal sharing of electrons causes a partial positive or negative charge for each atom. You can see that there. Well, water doesn't act in isolation, and I'm going to tell you that a beaker of water like this has trillions and trillions and trillions of water molecules, and they're all next to one another, and they're trying to figure things out. But they all have charges, these partial positive and negative charges. So let's draw this. Go ahead and press pause, get your piece of paper, flip it over if you need to, and draw this, what you see on the screen. And what I want you to get here is that they're lining up. You see how on the screen the partial positive charges of one water molecule are lining up with the partial negative charges of another water molecule. Let me do this. Just moving this so that you can see this other board. Essentially what I've drawn here is similar to what you're drawing right now. So I'm going to put a partial plus there and a partial negative there, and then I'm just going to put a dotted line between those two. This eventually, we're going to name this type of bonding. It's called hydrogen bonding. I'm going to write a partial negative there and a partial positive there, and I'm going to put a dotted line between that, similar to what you're drawing. Well, in living cells, we can, these electronegative atoms are usually oxygen and nitrogen atoms. If you remember Schnapps, there's a lot of O's and N's that are used in biology. So you can see, your book will give you an example of a nitrogen atom, which is also kind of over here towards the right-hand side. It has some electronegativity to it, and you can see how it will create kind of more of a partially negative portion of the ammonia molecule, the NH3 molecule. You can see that there, and then it's going to orient itself with a partial positive kind of side of one of these other oxygen. One of these other oxygen atoms that exist in a water molecule. It says a hydrogen bond forms when a hydrogen atom covalently bond to one electronegative atom is attracted to the electronegative atom of the other polar molecule.
Hydrogen bonding is a strong dipole-dipole attraction between molecules in which hydrogen is bonded to highly electronegative atoms, such as oxygen, nitrogen, and fluorine. Water is an example of a substance where hydrogen bonding occurs.
Hydrogen bonding occurs when a hydrogen atom is bonded to a small, highly electronegative atom, such as nitrogen, oxygen, or fluorine. In this example, its combination of high electronegativity and small radius enables fluorine to draw electron density away from the hydrogen atom. The HF bond is highly polar. Because hydrogen has no core electrons, its nucleus is left practically unshielded. This gives the hydrogen atom a relatively high partial positive charge, which is powerfully attractive to the partial negative charge on the fluorine atom of a neighboring HF molecule.
Okay, so that's the second type of bonding, hydrogen bonding, when they orient themselves like that. Go ahead and let's press pause and look in the mirror and tell yourself about hydrogen bonding, please. You can talk about covalent if you'd like also. Here we go. We're going to finish with ionic bonding. This is the third and final type of bonding here. So the kind of the garden variety example that's always given in general chemistry is sodium chloride. Sodium atom comes together with a chlorine atom, and they create an ionic compound after these things become ions. So I'm going to write ionic bonding up here. And the whole idea with ionic bonding is that one atom is going to lose an electron and another atom is going to gain an electron. And I'll try to teach you how to know who's going to lose one and who's going to gain one, but you might know this already. So this says transfer of an electron from sodium to chlorine. So you can see in that picture that literally an electron from sodium is going over to chlorine. I think this is fascinating because here's sodium in its elemental form. It's super reactive, and the reason why it's reactive is because, I'm getting a textbook here. It's way over here. It's in the same kind of row 7 with fluorine, chlorine. That's not true. Sodium's over here in this first kind of column that's going down. And the idea is that they only have one electron in their outermost shell, so they're unhappy. They either want to get rid of that in order to have a full outermost shell underneath it, or they need to gain, in our case, 7 electrons. Which is easier to do? Just get rid of one. And so that's why maybe in Mr. Vaughn's class or another chemistry teacher you've had, they put sodium in water and that creates sparks and stuff like that because it's super reactive. It's the same thing as chlorine. Chlorine gas is what's used at the Avon pool to clean it. And the reason why chlorine works is because it's way over here in this 7th row down. Same with fluorine, bromine, iodine. You've seen fluoride in your toothpaste. It has in it fluorine. You've heard about brominated pools, probably. Iodine is that kind of brown stuff that stains your skin purple if you're going to have a surgery done or something. The idea is all of these guys have 7 electrons in their outermost shell, and they just want one more. So that's why when you put fluoride on your toothpaste, on your toothbrush, and you brush your teeth, you can hear all the bacteria screaming and dying because electrons are being torn away from them to fill the outermost shells of the fluorine atoms that exist in the fluoride on your toothpaste, and that's why it's so good at killing things, just like chlorine in a pool. So I find it fascinating that there's something that can kill you, and then there's another thing that can kill you, and when you put them together, you get something as harmless as table salt. So yeah, we put it on popcorn. So let's do this. So go ahead and draw a sodium atom and a chlorine atom, and then create ions, and then put them together through ionic bonding. So press pause if you need to. Do this on a blank piece of paper, and I'll do it up here on the board. So here's the idea. I know that sodium is in the 3rd row down, 1, 2, 3. So it's going to have 3 electron shells, first shell, second shell, third shell. This is the nucleus here. I know that chlorine is in the third row down, so it's also going to have a nucleus, first electron shell, second and third. I know that sodium has one electron in its outermost valence shell, and I know that chlorine has 7, 1, 2, 3, 4, 5, 6, 7 electrons in its outermost valence electron shell. So let's fill those in. So here's what that looked like. Here's what this looks like for sodium: 2, 8, and then it just has 1 in its third shell, and it has an atomic number of 11. So I'm going to write up here 11 protons, or 11 p plus. That's what I've written there. So this has 11 protons and 11 electrons. If you count up the electrons, there should be 11 there. So when I draw the chlorine atom on the board, I know it has an atomic number of 17. I'll put up here 17 p plus. That's all I've written in there. And then I'm going to draw 2. So there should be 17 electrons there, as well as 17 protons. So if you look at this, if you do the math, both of these things are electrically neutral, as they are. But they're highly reactive because they're not happy. Neither of them have a full outermost valence electron shell. So what's the easiest thing to do? Either gain 7 or lose 1. So what the sodium atom does is it basically loses an electron. I'm just going to put it out there in space for a second. And then it has nothing in this outermost electron shell any longer. I'll just leave that electron right there. So now, does sodium have a full outermost electron shell? 1, 2, 3, 4, 5, 6, 7, 8. It's happy. The problem is that it still has 11 protons, and by definition, if the proton number changes, you change the atom. But in this case, the proton number hasn't changed, so we still have sodium. But if you count the electrons, we got rid of one of these. So we have 10 electrons, and if these are positive and these are negative, then what's our overall charge on a sodium atom in this state? Well, it's +1. That's why someone might say, well, a sodium atom has a plus charge. Well, let's see what happens over here. This guy has 17 total electrons. It has 7 in its outermost shell. It wants another one. There's one floating out here, so it's going to grab onto that. Now it has a full outermost valence electron shell of 8 electrons out here. So I'm going to put 18 here. Remember, the protons are positive, the electrons are negative. So what's the overall charge now on this chlorine atom? Has 1 extra. You know what, I'll just circle this because I don't want you to confuse it with the partial positive and negative charges earlier. So I'm just circling. So this has a positive charge, this atom does now. This atom now has a negative charge. Do negative and positives attract in nature? And the answer is yes. And so these things are actually going to stick together. So I'll show you what this kind of looks like. These are now called ions. This is a sodium ion. This is a chlorine ion. And then they're going to literally stick together. And you can see that there. That's a crystal of sodium and chlorine ions. And we call that sodium chloride and eventually table salt.
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bond.
Okay. Go ahead and take a moment and teach someone, either your mirror image or your favorite stuffed animal, about ionic bonding. Press pause. Finally, the last thing, they talk about chemical reactions because these things don't live in isolation. Even when they've created their molecules, they then react and make bigger and bigger molecules. And so here's an example of a chemical reaction. What you need to understand here is that there's reactants or starting molecules, and then there's products, and those are the final molecules. And sometimes reactions can go both ways, sometimes they can't, but the things that bind together are reactants, and then there are products on the right side. This is what I want you to think of when you think of any solution like this water or the table that you see in your room, or when two things come together. Just think of it as random bouncing together of all sorts of atoms are just bouncing and trying to bind together, and then things are sticking and things are breaking and so on. And I'm going to show you a movie about reactions and this thing called dynamic equilibrium.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No, well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there are lots of crazy stuff happening on the ground. You just need to zoom in and see it.
Okay, just know that sometimes there's, we're going to see this often in biology, there's a chemical equilibrium. When you see two arrows like that, it's just saying that the reaction is going in both ways. The products are becoming, the reactants are becoming products, and then the products are breaking back down to become reactants again. And again, we're going to see this a lot in biology. Well, chapter 2 is supposed to be easy. No websites, no learning targets. Thanks for listening.